Automobiles start losing value or depreciating as soon as they leave the car dealership. 5 years ago, a family purchased a new car that cost $16,490. If the car lost 13% of its value each year, what is the value of the car now? So we know our starting amount, but we need to decide what our growth factor is. The key here is that we're losing 13% of the value each year. So if we say 1 minus 0.13, because 13% as a decimal is 0.13, this means we're keeping 0.87, or 87% of the value each year. So our growth factor is going to be 0.87. Now we can write our equation, and this is going to be 16,490, which is our starting value, times our growth factor, 0.87, because it is keeping 87% of its value each year, and the exponent is going to be 5 because it's been 5 years. Now we can put that into a calculator, and we'll do the exponent part first. So 0.87 to the power of 5 equals approximately half. Now we'll multiply this by the 16,490, and the remaining value is $8,218. And since it's money, we'll round it. The 0 tells us to keep the 6 the same, so that's 96 cents. So the value 5 years after buying the car is still $8,218.96. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. The number of trees in a rainforest decreases each month by 0.5%. The forest currently has 2.5 billion trees. Write an expression to represent how many trees will be left in 10 years. Then evaluate the expression. So first we need to find our growth factor. If we are losing or decreasing by 0.5%, this is 0.005. So 1 minus 0.005 equals 0.995. It maintains 99.5% of the tree population. So this is going to be our growth factor. Write an expression to represent how many trees will be left in 10 years. Then evaluate the expression. So we have 2.5 billion as our starting amount. And we're going to multiply that by our growth factor, 0.995. Now, when we're writing our exponent, we have to be careful. We see the 10 years here, but this rate is done monthly. So we need to pay attention to that. So the exponent needs to be 12 months times 10 years. So this becomes 2.5 billion trees times 0.995 to the power of 120. We'll do the exponent first. We have 0.995 to the power of 120. And this is approximately 0.548. And now we'll do the multiplication part. This growth factor to its exponent times the 2.5 billion. And this comes out to approximately 1,369,000 or 369,965,000 and we'll round it to the nearest whole number because we're not going to count partial trees. So we'll say 714 because the 7 rounds the 3 up. So if the rainforest starts at 2.5 billion trees and loses 0.5% each month, then 10 years later, there will be just over 1.3 billion trees left. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. From 2005 to 2015, a population of P lions is modeled by the equation P equals 1,500 times 0.98 to the power of T, where T is the number of years since 2005. Number 1. About how many lions were there in 2005? So this equation represents 2005. So our beginning number of lions is the y-intercept, which is the number that does not have an exponent. So there were approximately 1,500 lions in 2005. Number 2. Describe what is happening to the population of lions over this decade. Well, the growth factor is 0.98. That means it is maintaining 98% of the population. If it is maintaining 98% of the population, it is losing 2% per year. And number 3, about how many lions are there in 2015? Show your reasoning. So we're going to use the function p equals 1,500 times the growth factor of 0.98. And if we want to know 2015, that is 10 years. So our exponent is going to be 10. The first thing we do is the exponent. So in a calculator, 0.98 to the power of 10. We'll round this to 0.82. Now we multiply that by the starting population of 1,500. And because we're talking about lions, we want to round to the nearest whole number. So we'll say 1,226 lions in 2015. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. A bank account pays 0.5% monthly interest. Number 1. If $500 is put in the account, what will the balance be at the end of 1 year, assuming no additional deposits or withdrawals are made? So number 1, this is an exponential function. We have our beginning amount, $500, times our growth factor. 1 represents maintaining the current amount. 0.005 represents the additional 0.5% monthly interest. Because this is monthly and the balance is at the end of 1 year, our exponent is going to be 12. By order of operations, we do the exponent first. So 1.005 to the power of 12 equals 1.062. And now we multiply that by the original 500. And that gives us $530. And because it's money, we're going to round it to 84 cents. Number 2. What is the effective annual interest rate? So the effective annual interest rate is referring to the monthly 1.005 done 12 times. And we said that this equaled approximately 1.062. As an interest rate, we want to translate this into the percentage interest. So we would move the decimal point 2 spots to the right, and we're going to say this is approximately 6.2% annual interest rate. Number 3, is the effective annual interest rate more or less than 6%, which is the nominal interest rate? The effective annual interest rate is more than 6%. It is 6.2%. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. The population of a city in 2010 is 50,000, and it grows by 5% each year after. Number 1. Write a function f which models the population of the city t years after 2010. So this is function f. The input is t. That equals the starting amount, 50,000, times the growth factor, 1 to maintain the current amount, 0.05 to represent the 5% increase, and the exponent is the input, which is t. Number 2. What is the population of the city in 2017? Well, 2017 would be 7 years later. So this would be f of 7 equals 50,000 times 1.05 to the 7th power. We do the exponent part first. 1.05 to the power of 7 is approximately 1.41. And now we multiply by the original amount, which was 50,000. And the new population is 70,355. Number 3. What will the population of the city be in 2020? Well, 2020 is 10 years later. So this would be f of 10 equals 50,000 times 1.05 to the power of 10. We do the exponent part first. 1.05 to the power of 10. And that equals approximately 1.63. Multiply that by the original 50,000, and that equals 81,445. Then they want to know, what about 2030? This would be 20 years later. So f of 20 is the original 50,000 times 1.05 to the power of 20. Do the exponent first. 1.05 to the power of 20. That equals 2.65. And multiply that by the original 50,000. And we get 132,665. Number 4. By what factor does the population grow between 2010 and 2020? What about 2020 and 2030? So first, we would take f of 10 and divide it by f of 0. So we said f of 10 was 81,445, and our starting amount was 50,000. This comes out to approximately 1.63. And we actually see that right there. Now we want to take f of 20 and divide it by f of 10. This would be 132,665, and we're going to divide it by 81,445. And this also comes out to 1.63. So we can see we had the exact same growth factor. That is the whole point of an exponential function. It is always being multiplied by the same amount. So if it's being multiplied for 1 year, it was being multiplied by 1.05. But every 10 years, that multiple is 1.63. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. A person charges $100 to a credit card with a 24% nominal annual interest rate. Assuming no other charges or payments are made, find the balance on the card in dollars after 1 year if the interest is calculated, number one, annually. So if we calculate it annually, then the entire 24% would be charged at that one time. So for number one, we would take $100, we would multiply it by 1.24. The 1 represents maintaining the $100. The 0.24 represents the 24% interest rate. And since there's only one charge, our exponent would be 1. And if we multiply $100 times 1.24, we get a total of $124. For number 2, now we're saying the interest is calculated every 6 months. So now we would have $100 times 1.12 squared. Now instead of charging 24% all at once, we're charging 12% twice. This becomes $100 times, we go to the calculator, 1.12 squared is 100 or 1.2544. And now when we multiply by $100, we get $125.44. Number 3. Now we're calculating it every 3 months. So we still start with the $100. But now when we multiply, every 3 months means we would make 4 payments. So 24% divided by 4 would be 6% each time. So we're going to say 1.06 is our growth factor, and our exponent is 4. So in the calculator, we're going to say 1.06 to the power of 4. And this comes out to 1.2625. Which when multiplied by 100 comes out to $126.25. Number 4, we're doing it monthly. So we still have the $100, but 24% divided by 12 months would be 2% per month. So that's 1.02 with an exponent of 12. And 1.02 to the power of 12 equals approximately 1.2682. So now when we multiply that by $100, we get $126.82. Number 5. This time we're looking at what happens if we calculated it daily. So now we're going to have 24%. So 0.24 divided by 365 days. And now we're going to add 1 to find our growth vector. So this is approximately 1.00066. And it's going to be to the power of 365 since we would be doing it daily. So now we can take this growth factor to the power of 365, and that's approximately 1.2711. And now when we multiply that by $100, we get $127.11. So you can see that even though it might have a 24% nominal annual interest rate, the more often that interest rate is calculated, the more money you actually end up paying. So if it's only calculated once per year, you would pay $124, but if it's calculated daily, you would actually end up paying $127.11. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. A couple has $5,000 to invest and has to choose between 3 investment options. Option A, 2.25% interest applied each quarter. Option B, 3% interest applied every 4 months. And option C, 4.5% interest applied twice each year. If they plan on no deposits and no withdrawals for 5 years, which option will give them the largest balance after 5 years? Use a mathematical model for each option to explain your choice. So first we have option A. In this, they start with $5,000. They're going to multiply by a growth factor of 1.0225. This is going to be applied each quarter, so that means 4 times a year times 5 years. So this becomes $5,000 times 1.0225 to the power of 20. We're going to do the exponent part first. So we have 1.0225 to the power of 20, and that equals approximately 1.56. And now we multiply that by the original 5,000. And this is worth $7,802 and 55 cents. Now we can look at option B. Again, we start with $5,000, but this time the growth factor is going to be 1.03 because it's 3% interest. And this is applied every 4 months, so that's 3 times per year times 5 years. Three times 5 makes the exponent 15. So now we'll multiply 1.03 to the power of 15. So this is approximately 1.56. And when we multiply this by the original 5,000, we get $7,789 and 84 cents. And lastly, we're going to look at option C. The same $5,000 initial deposit multiplied by a growth factor of 1.045. This is applied twice each year for 5 years. And 2 times 5 makes this an exponent of 10. So now 1.045 to the power of 10 is approximately 1.55. And when we multiply this by the original $5,000 deposit, we get $7,764 and 85 cents. So now if we look, which option gives them the largest balance after 5 years? That would be option A because it's $7,802.55. The more often that the interest is compounded, the larger it becomes. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. Elena says that 6% interest applied semi-annually is the same as 1% interest applied every month. She reasons they are the same because they are both a 12% nominal annual interest rate. Number one, is Elena correct that these two situations both offer a nominal annual interest rate? So for number one, yes, because 6% times 2 equals 12%, and 1% times 12 equals 12%. Number two, is Elena correct that the two situations pay the same amount of interest? So if we look, 6% interest would be 1.06, and that is paid out twice. So when we put this in the calculator, 1.06 squared is 1.1236. And that equals 12.36% interest. On the other hand, 1% interest is 1.01. And that's done 12 times, so the exponent is 12. Now when we put this in a calculator, 1.01 to the power of 12, we get 1.1268. Which equals 12.68% interest. So no, because 12.68% interest pays more than 12.3% interest. We call this effective interest. It's what actually gets charged. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. A bank pays 8% nominal annual interest, compounded at the end of each month. An account starts with $600 and no further withdrawals or deposits are made. Number one, what is the monthly interest rate? So for number 1, if I want the monthly interest rate, I take the 8% and I divide it by 12. So this becomes 0.08 divided by 12, which equals approximately 0.0067, which is approximately 0.67%. Number 2, write an expression for the account balance in dollars after 1 year. So we would start with the original $600. We would multiply that by 1.0067. The 1 represents maintaining the $600. The 0.0067 represents the monthly interest rate. And we would take that to the power of 12 because there's 12 months in a year. Number 3, what is the effective annual interest rate? To find this, we're going to take the 1.0067 to the power of 12. And now we get 1.083. So if we change this to a percent increase, then we have 8.3%. So while the nominal rate may be 8%, the effective rate is actually 8.3%. And number 4, write an expression for the account balance in dollars after T years. So for number 4, all we're going to do is take exactly what we wrote in number 2, the initial $600 times 1.0067 to the power of 12, but now we're going to add t onto that. So however many number of years, we'll need to multiply by 12 months, and then we'll take the 1.0067 to that exponent. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. At the end of each year, 10% interest is charged on a $500 loan. The interest applies to any unpaid balance on the loan, including previous interest. Select all the expressions that represent the loan balance after 2 years if no payments are made. So if we look at choice A, we have the original 500, but then what they do is they take 10% and apply it to the 500, and then they multiply it by 2 and add that to the original. So this is wrong because they apply the 10% to the original amount twice. And that's not what we're trying to do. On B, you see that we take the original 500, we multiply it by 1.1, which is multiplying it by the original and adding 10%. And then they multiply that new amount to add a 10% of the new amount. So B is correct. If we look at C, because they added 0.1 each time, they're not multiplying it to add 10%. They're just adding 0.1 twice. Now if we look at D, they've written it as an exponential formula. We have the original 500 times the growth factor of 1.1, because the 1 in the ones position maintains the $500, while the 0.1 adds 10%. But now we've made the exponent to, which means we apply that 10% to the original 500, and then we apply 10% to the new total. So D is correct. And finally on E, 10% of 500 is 50. So by adding 50, they're adding the first 10%, and then they're multiplying this new total by 1.1, which then adds 10% of the new total to it. So E is also correct. So choices B, D, and E are all different ways to write the exact same thing. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. A major retailer has a staff of 6,400 employees for the holidays. After the holidays, they will decrease their staff by 30%. How many employees will they have after the holidays? Since this is an exponential function, we're going to write it the same way we have been. We have our starting amount, 6,400. We're going to multiply that by our growth factor. If they decrease by 30%, then they maintain 70%. So that's 0.7. And then the exponent is just 1. They're only doing this once. So now anything to the first power is itself. We can multiply 6,400 times 0.7, and we get 4,480 employees. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. Here is a graph of the function f given by f of x equals 100 times 2 to the power of x. Suppose g is the function given by g of x equals 50 times 1.5 to the power of x. Will the graph of g meet the graph of f for any positive value of x? Explain how you know. So g of x has a y-intercept of 50, so it is going to start lower. It has a growth factor of 1.5, so it grows slower than f of x because it has a growth factor of 2. So they will never meet. If we wanted to prove it, it's going to start at 50. 50 times 1.5 is 75. Now 75 times 1.5 equals 112.5. If we multiply that by 1.5, we have 168.75. And we could multiply it one more time by 1.5, and we have 253. So as we thought, it's going to start lower, it's going to grow slower. They never meet. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. Here are the graphs of 3 equations. Y equals 50 times 1.5 to the power of x. Y equals 50 times 2 to the power of x. And y equals 50 times 2.5 to the power of x. Which equation matches each graph? Explain how you know. So all of them have the same y-intercept. What's different is the growth factor. The smaller the growth factor, the slower it grows. The bigger the growth factor, the faster it grows. So that means the slow graph, graph C, matches y equals 50 times 1.5 to the power of x, because the growth factor is the smallest. Next, we see graph B. Graph B is the middle graph. So graph B matches y equals 50 times 2 to the power of x, because the growth factor is in the middle. And finally, graph A grows the quickest, so it is going to match y equals 50 times 2.5 to the power of x, because it has the largest growth factor. If you have questions about how I solved any of the practice problems on these worksheets, please use class time now to ask for further clarification.